I'm Caitlin, and today I'm going to be doing a construction proof for the sine sum identity using this cute little graph. There's a bunch of different ways you could do it, but I just looked at my lecture notes and my professor's notes and a bunch of people explaining it online, and I came up with the best way to explain it that made sense to me, so I hope that it makes sense to you too. Yay, let's jump into it. Okay, so the first thing that I want to point out about the diagram is it's basically two main triangles. Triangle ADC, and its base is the hypotenuse of our bottom triangle, triangle ACB. And I really want to make sure that these triangles stand out to you because they're really important in our main objective, getting sine of x plus sine of y. So I'm going to outline them in red and blue. Okay, so now that that's done, I want to find all the angles that we'll need for the rest of the problem and get them out of the way. So we found these 90-degree angles at the bases of our triangles, and we've labeled them. And we're gonna need this angle right up here, and I know that it's y. And if you wanna know how I get that, this angle right here is a transversal to this angle right here. So AB and EC are parallel, and this line intersects, so I know that this angle and this angle are equal, so they're both y. And if I'm going to find this angle right here, I know that all angles of a triangle add up to 180. And since this angle right here is a 90-degree angle, it's going to be 90 minus y. And then I can think of it as 90 degrees plus y plus 90 minus y equals 180, okay? Or you could just think of it as that angle, we know it's y. Whatever works best for you. Okay, so now that we have everything labeled, get back to our main objective of finding sine of x plus y. So sine of these two angles added together. So we know that sine of x, or theta, is equal to opposite side over hypotenuse. I'll write it. So sine of theta is equal to our opposite side over our hypotenuse. So the side opposite of x plus y is this segment DF. So we know that sine of x plus y is equal to segment DF. Now, we can further take this big segment apart into smaller pieces. So we know that segment DE plus segment EF is equal to segment DF. So we can deconstruct it to say segment DE plus segment EF is the same as segment DF. Now, EF and CB are part of a rectangle, so they're exactly equal on this part. So I'm just going to say that segment DE plus segment CB are equal to DF, and therefore equal to sine of x plus y. Okay, so I'm just going to try and find as many lengths and sides that I can. So I'm just going to start with segment DC. DC is opposite of x, and it also has a hypotenuse of 1. So we're going to use sine. So sine of x is equal to DC over 1. And so it's just sine of x. Same thing with segment line AC. I have my line is adjacent to x, and I have a hypotenuse of 1. So I'm going to use cosine x. So cosine x is equal to AC over 1, and therefore it's just cosine x. All right, so with segment CB, it's opposite to y, and I have a hypotenuse of cosine x. So I know that sine of y is equal to segment CB over cosine x. And it's kind of starting to look a little, you might be able to connect that segment CB is equal to cosine x times sine of y. So, we know that CB is equal to cosine of x times sine of y. And we can kind of guess that DE is going to equal to sine of x times cosine y. So let's take a look and try and prove it. Okay, so we're working with segment DE. And DE is an adjacent to y. And we also have a hypotenuse. So obviously we're going to use cosine of y is equal to segment DE, our adjacent, over the hypotenuse, sine of x. And once again, just like before, we can figure that segment DE is equal to sine of x times cosine y. So, we've proven that segment DE is equal to sine of x times cosine y. So we just proved that segments DE and segment CB are equal to DF, which we know is equal to the sine of x plus y. And we proved that the sine, sum, trig identity is all good.